Now let's focus our attention on the projection matrix. What's going on here? Well, again, let's assume we're working in the case where the matrix X transpose X is invertible, which means X's columns are linearly independent. Then remember the vector that contains the optimal amounts to take of each one of X's columns is given by this, X transpose X inverse X transpose Y. Then the actual projection P of Y onto X's columns was X times this vector, because remember, this contains how much to take of each column. Now, when we actually go and take that amount of each column by doing X times W, that gives us X times X transpose X inverse X transpose Y. And the reason I'm doing this is because this gives us another perspective on what's going on here. So far, we've thought of this problem of projecting Y onto the column space of X as a question of how do I configure the right amounts of X's columns so that I make up Y as best as I'm able to. But there's another perspective. Notice, if I look at what's on the board here, this is really just some matrix, right? This ends up being a matrix that I'm multiplying Y by. What this means is that XW is equal to PY, which means I can interpret the act of projecting Y onto the column space of X as a linear transformation of Y, where the function, what it does is it doesn't stretch Y or it doesn't rotate Y or do any of those linear transformations. Rather, it projects Y. Right? The action is that it takes Y from living up here and it figures out where it should live down here, where this is the column space of X, and again, this is Y. That is the linear transformation. Okay? And the associated matrix P is this matrix, X times X transpose X inverse times X transpose. That is the projection matrix. Now, a question you always need to ask when you're dealing with a matrix who is defined in terms of a bunch of other matrices is, what is the shape of this matrix? Okay? Let's figure that out. X transpose X is a D by D matrix. So its inverse is also a D by D matrix. Okay, how did I find that? Well, X transpose is D by N, X is N by D, the inner dimensions collapse, and so I have a D by D. What is X? X is N by D. And what is X transpose? It is D by N. So these inner dimensions cancel those D's, and these inner dimensions cancel. And so P is an N by N matrix. Okay, which checks out because P is N by N, Y is N by 1, and so the output should also live in Rn, which it does here because these N's cancel. So my point in all of that is P is an N by N matrix.